Today we are going to discuss about minimum spanning tree algorithms. There are two types of minimum spanning tree algorithms are there. One is Prim's algorithm and second one Kruskal's algorithm. Today we are going to discuss about Kruskal's algorithm. Before that, what is a spanning tree? Spanning tree for a undirected graph. We are considering a undirected graph GVE. Then subtree is a subgraph of that graph, that is a tree. It containing all the vertices of that graph. For example, this is a graph. This graph uh, containing the spanning tree. Spanning tree means it's a tree. This graph containing a tree like this. That means there is no cycle in between that in the graph. Then here in this graph, all the vertices here A B C D E F V, these are the vertices. These vertices are connected by this edge. Then what is a minimum spanning tree? So here each edge has a weight. So weight of a subgraph is the sum of the weight of that its edges. So minimum spanning tree for a weighted graph is a spanning tree with minimum weight. So when we add the spanning tree edges, first we have a graph. From that graph we construct a tree with the minimum edges, and we sum up all the edges, then we will get a minimum weighted edge. That spanning tree is called minimum spanning tree. There are two algorithms are used to construct this minimum spanning tree. One is Prim's algorithm and second one is Kruskal's algorithm. Here the MST minimum spanning tree's weight is always minimized. Then the algorithm of Kruskal's and Prim's. In Kruskal's algorithm, we are considering a set A. A is a forest. We know that forest means it containing more than one trees. So when we add a self edge to A, is always a least weight edge in the graph that connect two distinct components. Suppose if this is a forest, here there are two edges are there, or there are two components are there. Then we connect these components. We check that whether there is a minimum weighted edge is there. If there is a minimum weighted edge is in there, then we will connect these two components. And safe edge means it does not form a cycle. In the case of a Prim's algorithm, there is a set A that forms a single tree. That is very important. In the case of a Kruskal algorithm, it is a forest, but in the case of a Prim's algorithm, it grows from a particular node and it grows adding each edge into that node, and it forms a single tree. So a safe edge is added to A is always a least weight edge connecting the tree to a vertex is not in the tree. So if a tree like this is A, we are considering this is A, and there is another edge. So if there is a minimum, we are checking that if there is a minimum weighted edge which is connected this tree into this edge, then we connect that least weighted edge. And here this vertex is not included in the tree, then only we can add this vertex into that tree. Otherwise, if is a already this tree containing this edge, then when we add this edge, it forms a cycle. So we can't add that. Then Kruskal's algorithm. So build this tree edge by edge. Here we consider an edge in the increasing order of the cost. If we selected edges will form a cycle, then discarded it, because this is a minimum spanning tree, so it doesn't containing a cycle. So when we try to add an edge into that forest, then it forms a cycle, then it discard that edge. This selection process continues until there are n minus 1 edges. If there are v vertices are there, or suppose if there are n vertices are there, so it forms a tree when it containing n minus 1 edges connected to that vertices. This is the MST-Kruskal algorithm. In this Kruskal's algorithm, we are passed the graph G and the corresponding edge weight W. Initially, our set A is set to infinity, and for each vertex V is belongs to V of a G. G is the graph, V is the vertex set in that graph, and we are considering each vertex in that graph. If there are 3 vertices are there, A, B, C, we are considering each vertex in that graph. And we perform a make set operation. That is, we are creating a individual vertices set. Then sort the edges of E. Then we consider the edges in that graph, and we sort all the edges in the non-decreasing order by weight W. So based on the weight, we are arrange all the edges in the non-decreasing order. That is means increasing order. Then for each edge UV belongs to E taken in non-decreasing order by weight. So then we consider the increasing order of each weight, and we check that find set of U and find set of V. If we are considering A and B, there are A is U and B is V. Then we check that if this belongs to same component. If it is same component, we can't add this. If it is in different component, that is find set of U and find set of V, these are in different component, then we can add this edge into A, U and V into A. That is here now it is containing an edge UV, and we union UV. Union UV means we are adding U and V as a single component. And this procedure is repeated for n minus 1 edges. Then return A. After completion of this procedure, we are returning from this. Then we will get a spanning tree. Then here A is infinity, so it take a time complexity order of 1. Then here for each vertex in this graph, so here we are taking a time of order of V, that is number of vertices in that graph. We are checking all the edges. Then here we are sort the edges. So sorting is a procedure. So sorting will take a time of E log E. If there are E edges, we are sorting the E edges. So E log E is the time complexity of sorting. Then if we use this loop, for each edge UV belongs to E, non-decreasing order of weight, and we are finding the find set, then this operation will take the time of order of E. That is, we are checking each edges. So total time complexity is order of E plus V into E log V. So we can consider it as a, here we find set operation are used. So it is a disjoint set height and path compression. So we will take this expression as a odd E plus V alpha V. This is a small value, so not consider. So here it will take E plus V. So total time will be E log E, or we can consider as V log V in the case of sparse edges. So E log V or E log E. That is the time complexity. Then example of a Kruskal's algorithm. ഇനി നമുക്കിവിടെ എന്താ ചെയ്യേണ്ടതെന്ന് വെച്ചാൽ കമ്പ്യൂട്ട് മിനിമം സ്പാനിങ് ട്രീ ആൻഡ് ഇറ്റ്സ് കോസ്റ്റ് ഓഫ് ദി ഫോളോയിങ് ക്രസ്കൽസ് അൽഗോരിതം, ഫോളോയിങ് ഗ്രാഫ് യൂസിങ് ക്രസ്കൽസ് അൽഗോരിതം. അപ്പോൾ നമ്മളിവിടെ നോക്കേണ്ടത് ഫസ്റ്റ് സ്റ്റെപ്പ് എന്ന് പറഞ്ഞാൽ 0 1 2 3 4 5 6 എഡ്ജസ് ആണുള്ളത്. അപ്പോൾ ഫസ്റ്റ് നമ്മൾ എന്ത് ചെയ്യണമെന്ന് വെച്ചാൽ ഇതിൻ്റെ വെയ്റ്റിൻ്റെ ബേസ് ചെയ്തിട്ട് സോർട്ട് ചെയ്യുക എന്നുള്ളതാണ് ഫസ്റ്റ് സ്റ്റെപ്പ്. അപ്പോൾ സോർട്ട് ചെയ്യുമ്പം ഏറ്റവും മിനിമം വെയിറ്റ് ഉള്ളതിനെയാണ് നമ്മൾ ആദ്യം കൺസിഡർ ചെയ്യുക. അപ്പോൾ ഇവിടെ ഏറ്റവും മിനിമം വെയിറ്റ് ഉള്ളത് ഏതാ ഉള്ളത്? ഈ എഡ്ജ് ഉണ്ട് 0 to 3. ദെൻ ഇവിടെ 5 ആണ് അതിൻ്റെ വെയിറ്റ്, ഇവിടെ 2 4 വെയിറ്റ്. അപ്പം നമുക്കിതിൽ ഏത് വേണമെങ്കിലും സെലക്ട് ചെയ്യാം. ഫസ്റ്റ് ഞാൻ 0 to 3 ആണ് സെലക്ട് ചെയ്യുന്നത്. ദെൻ 2 to 4 ആണ് സെലക്ട് ചെയ്യുന്നത്. അപ്പോൾ രണ്ടും ഡിഫറെൻറ്റ് കോമ്പണൻറ്റാണ്. ഒന്ന് 0 to 3 വരും, വെയിറ്റ് 5. ദെൻ നെക്സ്റ്റ് 2 4 5, രണ്ടും ഡിഫറെൻറ്റ് കോമ്പണൻ്റ് ആണ്. സോ ഇവിടെ ഫസ്റ്റ് 0 to 3 സെലക്ട് ചെയ്യുന്നു. ദെൻ 0 to C ഇവിടെ കൺസിഡർ ചെയ്യുന്നു. നെക്സ്റ്റ് സ്മോളസ്റ്റ് വെയിറ്റ് എന്ന് പറയുന്നത് ഈ എഡ്ജാണ് വരിക, 2 to 4. ദെൻ അതിൻ്റെ വെയിറ്റ് എന്ന് പറയുന്നത് 5 ആണ്. സോ നമ്മൾ നെക്സ്റ്റ് വെയിറ്റ് 2 5 സെലക്ട് ചെയ്യുന്നു. ദെൻ നെക്സ്റ്റ് വെയിറ്റ് മിനിമം വെയിറ്റ് ഏതാണ് വരുന്നത്? ഹിയർ 6 വെയിറ്റ് ഉള്ള എഡ്ജ് എന്ന് പറഞ്ഞാൽ 3 5 ആണ്. സോ നെക്സ്റ്റ് സ്റ്റെപ്പിൽ വി ആർ സെലക്ടിങ് 3 5 കണക്ട് ചെയ്തു. നമ്മൾ ഓരോ ടൈമും കണക്ട് ചെയ്യുമ്പോൾ ചെക്ക് ചെയ്യും ഇഫ് ഇറ്റ് ഈസ് ഫോം എ സൈക്കിൾ. ഇവിടെ ഒന്നും സൈക്കിൾ ഫോം ചെയ്യുന്നില്ല. നെക്സ്റ്റ് ടൈം മിനിമം എഡ്ജസ് ആർ either we can select 0 1, that is 7, and wait 1 4. ഏത് വേണമെങ്കിലും സെലക്ട് ചെയ്യാം. ചെക്ക് ചെയ്യുക 0 1 4 സെലക്ട് ചെയ്യുമ്പോൾ ഇതൊന്നും വരില്ല. അല്ലെങ്കിൽ നമുക്ക് 0 1 സെലക്ട് ചെയ്യാം. ഏതാണെങ്കിലും ഒരെണ്ണം സെലക്ട് ചെയ്യുക. സോ ഹിയർ വി ആർ സെലക്ടിങ് 0 1, that is here it is selected. Then next minimum edge ഏതാണ്? 1 4. So if 1 4 connected, there is no problem, there is no cycle. So we will connect 0 4. The next weight, minimum weight is 8. Either we can select this one or this one. 1 2. If we select 1 2, then it form a cycle. So we can't add this edge. So another weight is 4 5. If we connect 4 5, then it forms a cycle like this. So we can't add this edge. So that is shown here. We are selecting 4 5. Then it forms a cycle. So we can't connect. Then if we select 1 2, it's also forms a cycle. We can't add that edge into this. Then next 9 is 4 6. When we select 4 6, it has no problem, it does not form a cycle. So we can add that edge. Then now all the vertices are connected by an edge. So we can stop here. If we try to add any of the edge, it forms a cycle. Suppose 9, if 3, 1. When we connect 3, 1, it forms a cycle. So it does not have minimum spanning tree. If we try to next one is 11, 5, 6. If we connect this one, it forms another cycle. So we can't add. Then 3, 4. 3, 4, if we connect this, it forms a cycle. So we can't add that edge into this tree. So now we will stop here. Then minimum spanning, cost of that spanning tree. How to calculate? We are adding all the edge weight. So what is that? 6 plus 5, 11. 11 plus 7, 18. 18 plus 7, 25. 25 plus 5, 30. 30 plus 9, 39. So total cost is 39. So this is the minimum spanning tree of that graph. Thank you.